Good evening, ladies and gentlemen. How are you all doing this evening? How was your recess? I know too short, and yes, Mr. Melville, it is just sort of like a study break. Why bad? This week has been too long. Too long already, only on Monday. But at least you guys got a recess. I didn't have a recess. I just continued working. So let's wait another minute or two and wait for more of our friends to join us. But while we are waiting, it seems like I'm going to preach to the choir again because I've been really receiving some really stupid questions about the moon assignment. Stuff I have already discussed in class, showed examples in class. I showed you websites to find data in class. I told you guys not to underestimate projects. I told you guys what to do when you run into problems, and still I get stupid questions. And when I try and look at class participation, because I can see who participates in the online classes, I can see who watched the videos on Blackboard Collaborate, who downloaded it from Blackboard Collaborate. I can see who watched the videos from Google Drive, who downloaded it from Google Drive. And I can see who watched it on YouTube. The last lecture, so lecture 12, part 1, that's been up for almost 2 weeks now. There has only been 4 downloads for that lecture across all platforms. And there's only been 6 views for that lecture on all platforms. So, what is going on, everyone? Are you not participating in my class? Are you not watching what's going on? If that trend continues, then I will remove all lecture slides from ClickUp. I will remove all lecture videos. And the only information you will get is via participating in the online classes. And those students that already reached out to me asking for help with their assignments, asking good questions about assignments, I'm very proud of you guys because I know you guys are actually thinking about the assignment. You are paying attention, you are working very hard, and that makes me happy, and well done to you guys. Well done to the students that's actually made appointments to come and see me for help with the assignment. Well done. But if I'm looking at who's in the class right now, I'm actually preaching to the choir because with everyone online in a class, you're all doing very well. So that means there are people not paying attention. We are currently around about 170 students registered for this module, and we are 53 online in this class. And in the next week, probably another 20 is going to watch the recorded videos. So there is a problem. I will send out an email on this matter as well as WhatsApp, and as well on Discord. So just to remind you guys, tomorrow I will be on campus. I will be there about 9:30. I will be on campus until about 1:30. I have another meeting starting at 3 off campus that I need to prepare for. So I'll be there from 9:30 to about 1:30. So if you have any problems, any questions, you're more than welcome to pop in during those times. Otherwise, you're more than welcome to set up a consultation session. And that's it. That's me finishing my rant. Before we start off with tonight's lecture, do you guys have any questions? Anything I can assist with? No, you don't have to make an appointment to pop in tomorrow. So when I'm on campus, I have an open door policy. As long as I'm there, you are more than welcome to pop in anytime. Pleasure. And if you would like to have more consultation sessions, if you'd like me to be more on campus, just send me an email. You can send WhatsApp as well, but I prefer email as communication language because it just makes it easier to start a paper trail if I need to escalate something to the HOD or to the dean. So that just makes it a bit easier. But if I'm on campus, you guys are more than welcome to pop in anytime. If you're off campus and you want a video consultation, I'm available on all platforms of video consultations. You can do Zoom, you can do Skype, we can do Google Meets, we can do Microsoft Teams. We can even do a WhatsApp video call. So if you need consultation, I'm here to help you make use of it. So do you know what caused the heavy rains and flooding in KZN? So one contributing factor is the El Nino effect we are currently in. So the El Nino effect means we are now in a period we have abnormal amounts of rainfall. And that is one of the contributing factor to the floods in KZN. Pleasure. Before we continue, if you guys have any interesting science news you can share, of something interesting happening currently right now in the science world, and especially in the astronomy world. So yes, there are two. So the one is made history, the first time ever a solar eclipse was observed from a different planet. And yes, the Curiosity rover observed a solar eclipse from Mars. That was very cool. And then, yes, the alignment of planets. So right now in the morning, you'll probably still be able to see it this week. Just after 5 in the morning, there's actually a planetary alignment where Mercury, Venus, Mars, Jupiter, and Saturn and the Moon is actually now lining up. That is also very beautiful to see. So some planetary alignments happen quite often, especially with the planets closer to the sun. But this one is actually very cool to see. On our groups, I will post photos of it that a few of my colleagues has taken. And something exciting, the LHC, Large Hadron Collider, turned on from this week again. It had been undergone maintenance for the last 3 years. And now it's been turning back on to start doing experiments again. And one thing they are going to try to look for in this experiments is dark matter and dark energy. So that is also very cool and something worthwhile. So before recess, we ended off right about here where we discussed the structure of galaxies. So if we look at head on, we can see the central bulge. The sun is located out here, and this is the disk. If you look at side on, here we can see globular clusters, the halo, the central bulge. Is everybody still happy with this? Everybody still following? Everybody okay with where we stopped? And now we're going to continue again. So next important question is, how do we determine the mass of the galaxy and what is in the mass of the galaxy? So to find the mass of an object, astronomers must observe the motion of another object orbiting it. Just in a binary star system, so humans don't live long enough to see stars moving significantly along their orbits around the galaxy. But astronomers can observe the radial velocities, proper motions, and distances of stars, and then calculate the sizes and periods of their orbits. The results can reveal the mass of the galaxy. Stars in the disk of the galaxy follow nearly circular orbits that lie in the plane of the disk. Current observations indicate that the Sun orbits the center of our galaxy at about 225 kilometers per second, moving in the direction of Cygnus. The evidence suggests the Sun's orbit is nearly circular. So given the current best estimate for the distance to the center of our galaxy, and that is 8.3 kiloparsecs, you can find the circumference of the Sun's orbit by multiplying by 2. If you divide the circumference of its orbit by its orbital velocity, you will discover the Sun has an orbital period of about 225 million years. The radius of the Sun's orbit around the galaxy is 8,300 parsec, and each parsec equals 2.1 times 10 to the power 5 astronomical units. Multiplying, you find the radius of the Sun orbit is 1.7 times 10 to the power 9 astronomical units. So the orbital period is 225 years. So that means the mass mass is 1 times 10 to the power 11, so 100 billion solar masses, the mass of the Sun. This is only a rough estimate because it does not include any mass laying outside the orbit of the Sun. Allowing for that overlooked mass yields a lower limit to the total mass of a galaxy of at least 400 billion solar masses. The rotation of a galaxy is actually the orbital motion of each of its stars around the center of mass. Stars at different distances from the center revolve around the center of the galaxy with different periods. So stars starting near each other will draw apart as time passes, a situation called differential rotation. The differential rotation of the galaxy means that stars at different distances from the center have different orbital periods. In this example, the star just inside the Sun's orbit has a shorter period and pulls ahead of the Sun, while the star outside falls behind. To fully describe the rotation of our galaxy, astronomers graph orbital velocity versus radius to produce a rotation curve. The rotation curve of our galaxy is plotted here as orbital velocity versus radius. Data points show measurements made by radio telescopes. Observations outside the orbit of the Sun are much more uncertain, and data points scatter widely. Orbital velocities do not decline outside the orbit of the Sun, as you would expect if most of the mass of the galaxy were concentrated toward the center. Rather, the curve is approximately flat at great distances, suggesting that a galaxy contains significant mass outside the orbit of the Sun. If all of the mass of the galaxy were concentrated near its center, you would expect to see orbital velocities decrease as you move away from the center. That is what you see in our solar system, where nearly all of the mass is concentrated in the Sun. For that reason, it is called a Keplerian motion, referred to Kepler's laws. In contrast, the best observation of the rotation curve of the Milky Way showed that orbital velocities in the outer disk are constant or even increasing with distance from the center of the galaxy. Those high orbital velocities indicate that the larger orbits enclose more mass and imply that our galaxy has much more mass than is contained within the radius of the Sun's orbit. Both observational evidence and mathematical models show that the extra mass lies in an extended halo, sometimes called the galactic corona, that may reach out to 10 times further than the edge of the visible disk and could contain more than 1 trillion solar masses. Most of that mass is invisible, neither emitting nor absorbing light, so astronomers refer to it as dark matter. Some of the mass in the galactic corona is made up of low luminosity stars and white dwarfs, but much of the mass must be some other form of matter. The most striking feature of galaxies like the Milky Way is their patterns of spiral arms that wind outward through the disk. These arms contain swarms of hot blue stars, clouds of dust and gas, and young star clusters. The young object suggests that the spiral arms involve star formation. But as you try to understand the spiral arms, you need to consider two problems. First, how can anyone be sure our galaxy has spiral arms if interstellar dust obstructs our view? And secondly, why doesn't the differential rotation of the galaxy destroy the arms? The solution to both problems involve star formation. As you have already learned, O and B stars are often found in associations and are very luminous. Thus, they are easy to detect across great distances. Unfortunately, at those great distances, the parallaxes are difficult to observe. The available data indicate that OB associations near the Sun are not located randomly, but lie along several spiral arm segments. So here we can see the galactic centers this way. This is the Sagittarius arm, the Orion Cygnus spur, and the Perseus arm. Here's where the Sun is located, and here we can see where other stars are. So here in image A, we can see nearby young O and B stars in a galaxy fall along bands that appear to be segments of spiral arms. And then in image B, many of the galaxies in the sky are disk-shaped like our galaxy. Most of those galaxies have spiral arms marked, especially by hot luminous stars and emissions nebula that must be very young. This might cause you to suspect that the spiral arms are related to star formation. Then in image S, we can see images of other galaxies show spiral arms that are especially prominent and well defined. Those spiral segments have been named for the prominent constellations through which they pass. Astronomers can now use infrared and radio telescopes to penetrate the interstellar dusk, locate more distant OB associations, and trace the spiral arms even further. Objects used to map spiral arms are called spiral traces. Aside from OB associations, spiral traces include young open star clusters, clouds of hydrogen ionized by hot stars, so this means emission nebula, and certain high-mass variable stars. So notice that all spiral traces are young objects formed recently, astronomically speaking. O stars, for example, live for only a few million years. The typical orbital velocity is about 200 kilometers per second, so they cannot move more than about 500 parsecs in their lifetimes. This is less than the width of the spiral arm. Because they don't live long enough to move away from spiral arms, they must have formed there. Studies of other galaxies show that their spiral arms are also marked by hot blue stars and other spiral traces. The youth of spiral traces is an important clue about spiral arms. Obviously, spiral arms are associated with star formation. Before you can follow this clue, you need to extend your map of spiral arms to show the entire galaxy. So this brings us back to this image. So here we can see again our spiral arms is and where these OB stars lay. Is everyone still following? Awesome. So question, does the model account for the light from the back of the spiral taking longer to reach us than the front? Yes, it does. And that is something we are going to discuss in a couple of slides. Radio astronomers use the strong spectral line emissions from carbon monoxide to map the location of giant molecular clouds in the plane of the galaxy. The dust that blocks our view at visual wavelengths is transparent to radio waves because radio wavelengths are much larger than the diameter of dust particles. Recall from Chapter 9, Section 2 that giant molecular clouds are sites of active star formation. If you point a radio telescope at a section of the Milky Way, you will receive a combination of signals from gas clouds in the direction you are looking that lie at various distances across the galaxy. Signals from those different clouds can be separated by measuring the Doppler shifts of the spectral lines. Astronomers then use a simple model of orbital velocities at different distances from the center of the galaxy in order to untangle the observations and locate the individual clouds. Maps constructed from such observations reveal that the giant molecular clouds, like OMB stars, are located along segments of spiral arms. So here we can see an image A. At a wavelength, spectral lines emitted by carbon monoxide particles, astronomers find many molecular clouds along the Milky Way, but the clouds overlap in a confusing jumble. By using a model of the rotation of a galaxy to interpret the radial velocities of the clouds, radio astronomers can estimate the distances to each cloud and use them to map spiral arms. Then in image B, this map represents the view from 0.2 kiloparsecs directly above the Sun. The molecular clouds shown here as hemispheres extending above the plane of our galaxy are located along spiral arms, so angle labels indicate the galactic longitudes. As you learn in Chapter 9, Section 1, especially Figure 9.3, observing at a wavelength of 21 centimeters allowed the detection of a spectral line of atomic hydrogen. That type of gas is generally warmer than the material in molecular clouds. Just as for the molecular clouds, that type of gas is generally warmer than the material in molecular clouds. Just as for molecular clouds, analysis of the atomic cloud radial velocity data requires that astronomers start with estimates of the orbital velocities at the different distances from the center of the galaxy. The atomic hydrogen map doesn't trace as clear a spiral pattern as the molecular gas, in part because the warmer atomic gas has more random motions due to its temperature, as well as turbulence within the clouds that distort the radial velocities. So in this image, we can see the 21 centimeter radio map of galaxy confirms the concentrations of neutral atomic hydrogen gas lie approximately in spiral, but the pattern is complex and suggests branches and spurs. Observations toward the center of the galaxy have an additional problem. The orbital motions of gas clouds are perpendicular to the line of sight, and all of the radial velocities are zero. That is why the map in Figure 12.14 is empty in a wedge-shaped region directly towards the center. Clearly, we live in a spiral galaxy, but a spiral pattern appears to be slightly irregular, with many branches and gaps. The stars you see in Orion, for example, appear to be in a detached segment of a spiral arm, referred to as a spur. By combining observations of our own galaxy with studies of other galaxies. Astronomers can make educated guesses about what a Milky Way galaxy might look like viewed from outside. So here we can see an estimate of what our own galaxy would look like. So this is a two-armed model for the Milky Way, and it's based on observations with the Spitzer infrared telescope. So notice the large central bar. And here we can see branches and spurs are common in this model, and the sun should be around about here. In addition to helping map the arrangement of spiral arms, infrared observations indicate that a central bulge of a galaxy is not a sphere but rather an elongated bar pointing partially away from Earth. In the next chapter, you will see that such structures are common in other galaxies. One important fact revealed by the radio maps is that spiral arms are regions of higher gas density. Spiral traces tell you that arms contain young objects, so you suspect they must also have active star formation. Radio maps confirm your suspicion by telling you that the material needed to make stars is abundant and concentrated in spiral arms. Having mapped the spiral pattern of our galaxy, and seeing these patterns in other galaxies, you might ask, just what are spiral arms? You can be sure they are not physically connected structures like bands of magnetic field that hold the gas in place. If they were, the differential rotation of a galaxy would destroy them within just a few 100 million years, winding them up and then tearing them apart like paper streamers caught on a wheel of a spinning car. Yet spiral arms are common in galaxies, so they must last for billions of years. Astronomers conclude that spiral arms are dynamically stable. They retain some appearance, even though the gas, dust, and stars in them are constantly changing. To see how this works, think of a traffic jam behind a slow-moving truck. Seen from an airplane, the traffic jam would be stable, moving slowly down the highway. But you could watch an individual car approach from behind, slow down, wait its turn, finally reach the front of the jam, pass at the truck, and resume speed. The individual cars in a jam are constantly changing, but a traffic jam itself is a stable pattern, moving at its own speed along the highway. In the spiral density wave theory, spiral arms are dynamically stable regions of compression that move slowly around the galaxy, just as the truck moves slowly down the highway. Gas clouds moving at orbital velocity around the galaxy overtake the slow-moving arms from behind and slam into the gas already in the arms. The sudden compression of the gas can trigger the collapse of the gas clouds and the formation of new stars. So here we can see a representation of this. So newly formed stars in the remaining gas eventually move on through the arm and emerge from the front of the slow-moving arm to resume their travels around the galaxy. So here we can see orbiting gas clouds overtake the spiral arm from behind. So we can see the gas cloud, the galactic center, the spiral arm. The compression of a gas cloud triggers star formation. So here's massive stars and lower mass stars. Massive stars are highly luminous and make the spiral arm prominent. The most massive stars die quickly. Low mass stars live long lives but are not highly luminous. So according to the spiral density wave theory, star formation occurs as gas clouds are compressed when they pass through the spiral arms. What evidence do astronomers have that star formation is caused by spiral density waves? Spiral traces are the key. Stars of all masses are forming in spiral arms, but as you already learned, the O and B stars live short lifetimes that die before they can move out of the spiral arm. These massive high luminosity stars, along with gas and dust, confirm that spiral arms are sites of star formation. You can expect that lower mass stars like the Sun can't be used as spiral traces. They also form in spiral arms, but during their relatively long lives, they leave the arms in which they were born. The sun probably formed as part of an association in the star-forming region within a spiral arm almost 5 billion years ago. Escaped from that association and has circled the galaxy more than 20 times, passing through many spiral arms. Plotting the locations of sun-like stars does not reveal the spiral pattern, confirming this picture. The evidence seems to fit the spiral density wave theory well, but the theory has two problems. Firstly, how does the complicated spiral distribution begin, and how is it sustained? Computer models indicate that spiral density waves should slowly die out in about 1 billion years, so something must generate a spiral wave. Mathematical models show that a disk of a galaxy is naturally strongly affected by certain types of disturbances. As you learned earlier, observations show that the center of our galaxy is not a sphere but a bar. The gravitational effects of the bar's rotation could continuously perturb the galaxy's disk and stimulate the formation of spiral density waves. A close encounter with a passing galaxy could also stimulate a spiral pattern. Some galaxies without a visible bar or large companion nevertheless have prominent spiral arms. So astronomers continue to make observations and computer models investigating the questions of spiral arm formation. The second problem is for the density wave theory involved the spurs and branches observed in the arms of our own and other galaxies. Some galaxies called grand design galaxies have a symmetric two-armed patterns. Other galaxies have a great many short spiral segments, giving them a fluffy appearance, but no overall grand design. These galaxies have been termed flocculent, meaning woolly. So our Milky Way galaxy seems to be intermediate between extremes of flocculent versus grand design. What process might make small-scale spiral segments instead of a galaxy-wide spiral pattern? The answer may lie in self-sustaining, so contagious star formation. So here we can see in image A, some galaxies are dominated by two spiral arms, but even if those galaxies minus spurs and branches are common, spiral density waves can generate a two-armed grand design pattern. That self-sustained star formation might be responsible for irregularities. In image B, many spiral galaxies do not appear to have prominent spiral arms. Abundant spurs and branches nevertheless suggest that star formation is proceeding robustly in such galaxies. Observations indicate that our Milky Way galaxy spiral pattern is intermediate between these two examples. So the answer may lie in self-sustaining, so contagious star formation. So you learned in chapter 9, section 2, that star formation is one location can lead by supernova explosions, stellar wind, and outflows to star formation in neighboring locations. Look back especially to figure 9.9. The differential rotation of the galaxy will drag the inner edge of star-forming cloud ahead and let the outer edge lag behind. This will result in a region of star formation shaped like a segment of spiral arm, so a spur. So here we can see differential rotation drags the inner edge of a gas cloud ahead of its outer edge. A cloud can become elongated by continuing differential rotation. Star formation in a gas cloud can produce massive stars whose high luminosity, and supernova explosions can compress surrounding gas and trigger more star formations. If star formation continues long enough, a cloud can be elongated in a spiral segment. So self-sustaining star formation may be able to produce long clouds of young stars that look like segments of spiral arms. Astronomers suspect that while a spiral density wave can generate beautiful two-arm patterns, the self-sustaining star formation process produces the branches and spurs so prominent in some galaxies, including our own. This discussion of star formation in spiral arms illustrates the importance of natural processes. The spiral density wave creates graceful arms, but it is the star formation and the arms that makes them stand out so prominently. Self-sustaining star formation can act in some galaxies to modify the spiral arms and produce branches and spurs. In other galaxies, it can make the spiral pattern flocculent. By searching out and understanding the details of such natural processes, astronomers can begin to understand the overall structure and evolution of the universe we live in. The most mysterious region of our galaxy is the very center, the nucleus. At visual wavelengths, this region is totally hidden by dust and gas that dim the light it emits by 13 magnitudes. So if a trillion photons of light left the center of the galaxy on a journey to Earth, only one of those photons would make it through the dust and the gas. Consequently, visual wavelengths images reveal nothing about the nucleus. Observations at infrared and radio wavelengths can see through the interstellar material, and those images show a region of tremendously crowded stars orbiting the nucleus at high velocities. To understand what is happening in the innermost regions of a galaxy, you need to carefully compare observations and hypotheses. So one branch of astronomy is called active galactic nuclei. It actually studies the nucleus of galaxies. One of my colleagues is an expert on this. But what would you guys guess is the mechanism in the center of our own galaxy or in most galaxies? Yes, a black hole. You guys are correct. And how would you guess does a black hole, or why is a black hole important in the center of galaxies? So yes, Ms. Malvo, you're right. We're also leading up to discussion on quasars. So yes, gravity. It causes the stars in a galaxy to orbit a central point and keep everything together. So if you look up at the Milky Way on a dark night, you might notice a slight thickening in the direction of the constellation Sagittarius, but nothing specifically identifies this as the direction of the heart of the galaxy. Even Shapley's study of globular clusters identified the location only approximately. The first complete infrared map of the central bulge, made by Eric Becklin in 1968, showed the location of the intense radiation where the stars are most crowded together, the gravitational core of the galaxy. So high-resolution radio maps of that stellar center has revealed a complex collection of radio sources, with one Sagittarius A, abbreviated SGRA, and usually pronounced Sag-A star, laying at the exact location of the galactic nucleus. Radio interferometer observations show that Sag-A star is less than 1 astronomical unit in diameter, but nevertheless a strong source of radio energy as well as X-ray emissions. There are 3 important points to consider when we talk about this. And the first thing is, observations at radio infrared wavelengths reveal complex structures near Sag-A star, caused by magnetic fields and by rapid star formation. Supernova remnants show a massive stars has formed there recently and exploded at the end of their lives. And secondly, the center is very crowded. Tremendous numbers of stars heat the dust, which emit strong infrared radiation. And then lastly, there is evidence that such a star is a supermassive black hole in which gas is flowing. Observations of the motions of stars orbiting the central object indicate its mass is about 4 million solar masses. And that is right in the ballpark of a supermassive black hole. The supermassive black hole is an exciting idea, but scientists must always be aware of the difference between adequacy and necessity. A supermassive black hole is adequate to explain the observations, but is unnecessary. Could there be other explanations? For example, some astronomers have suggested that gas flowing inward could trigger tremendous bursts of star formation, causing some of the turmoil observed in the galactic nucleus. Such hypothesis has been considered and tested against the evidence, but none appears to be adequate to explain all the observations. So far, the only viable hypothesis is that our galaxy nucleus is home to a supermassive black hole. Meanwhile, observations are allowing astronomers to refine their models. For instance, such a star is not as bright in X-rays as it should be if it has hot accretion disk with matter constantly flowing into the black hole. Observations of X-ray and infrared flares lasting only a few hours suggest that a mountain-sized blobs of matter may occasionally fall into the black hole and be ripped apart and heated by tides. The black hole seems to be mostly dormant, lacking a fully developed hot accretion disk because little matter is flowing into it at the present time. Such a supermassive black hole could not be the remains of a single dead star. It contains too much mass. It probably formed when the galaxy first formed 13 billion years ago. In later chapters, you will see that such supermassive black holes are found at centers of most large galaxies. So, what is the origin and history of the Milky Way galaxy? So just as dinosaurs left behind fossilized footprints, our galaxy has left behind clues about its youth. Astronomers have compelling evidence that the stars of the spherical component are old and must have formed long ago, when the galaxy was very young. Some of that evidence comes from comparing abundances of chemical elements in stars located in different parts of the galaxy. So if you're ever in a dark place and you can see this band of the Milky Way, this is in the direction of Sagittarius. So this is looking towards the center of the galaxy, and because it's more crowded, you can see more stars in this direction. So you can recall what you have learned about stellar structure and stellar evolution. In previous chapters, you understand the chemical evolution of the galaxy. In astronomy jargon, the term metals refer to all of the chemical elements heavier than helium. In a later chapter, you will learn about evidence that when the universe began, it contained about 90% hydrogen atoms, 10% helium atoms, and little or no metals. The first stars that formed early in the universe's history therefore had to be nearly pure hydrogen and helium. All of the other chemical elements have been produced by nucleosynthesis, the process in stars that fuses hydrogen and helium to make the heavier atoms. As you already know, medium mass stars like the Sun cannot ignite carbon fusion, but during helium fusion, the heat and density can trigger some nuclear reactions that cook the gas to produce small amounts of elements heavier than helium. When an aging star pushes away its surface layers to produce a planetary nebula, some of those elements are spared back into the interstellar medium, where they may become part of newly forming stars and planetary systems. So lithium is a metal in astronomy. Yes, that's exactly true. So the most massive stars fuses elements up to iron and simultaneously cook the gas in the core through small amounts of many different atoms, including sulfur and calcium. When those stars die in a supernova explosion, traces of those elements are spread back into the interstellar medium, along with rarer atoms such as gold, platinum, and uranium produced in the supernova explosion itself, which can also be incorporated eventually into new stars and planets. Nevertheless, metals are actually quite rare in the universe. Conventionally, astronomers graph the abundance of the elements using an exponential scale. But if you replot the data using linear scale, you can see how rare these atoms actually are. So here we can see the abundance of chemical elements in the universe. So in image A, when the elemental abundances are plotted on an exponential scale, you see that elements heavier than iron are about 1 million times less common than iron, and that all elements heavier than helium, so the metals, are quite rare. And then in image B, here we can see the same data plot on a linear scale provides a more realistic impression of how rare metals are. Carbon, nitrogen, oxygen make small peaks near atomic mass 15, and the peak representing iron is just visible in this graph. So here is the peaks we can see here. So hydrogen, helium, carbon, nitrogen, oxygen, iron, elements heavier than iron. But if you plot it linearly, here we can see hydrogen, here we can see helium, carbon, the little blob here is iron, and so on. So here you get an idea how rare these elements actually are. Question, so how would the bulge of our galaxy initially form? Or would a black hole be the connection point? But to my knowledge, there are things older than the black hole in the center of our galaxy. If it were to be a black hole that resides there. So that is a very, very, very good question. So we will now in a couple of slides discuss how the bulge of the galaxy is formed. And we will also touch on a few objects that's older than a black hole. But the black hole is key to a few of these, but we will discuss that momentarily. So in the 1940s, astronomers realized that there are two families of stars in the galaxy. They form and evolved in similar ways, but they differ, especially in the abundances of metals. Population 1 stars are metal-rich, containing 1 to 3% metals, whereas population 2 stars are metal-poor, typically containing less than 0.1% metals. The difference is clearly evident in their spectra. So here is another question for the test in exams. I can ask you what is a population 1 star and what is a population 2 star, what are the differences. So this is just a hint and tip to keep in mind. So here we can see in image A, the difference between spectra of population 1 stars and population 2 stars is dramatic. Examine the upper spectra here and notice the hundreds of faint spectral lines. The lower spectrum has fewer and weaker lines than in image B. A graph of such spectra reveals overlapping absorption lines of metal completely blanketing the population 1 spectrum. The lower spectrum is that of extremely metal-poor star with only a few weak metal lines of iron and nickel. This population 2 stars contain about 10,000 times less metals than the Sun. Do you reckon that a universe is currently in a black hole? I don't think so. So HR diagrams of star clusters reveal that population 1 stars are relatively young and population 2 stars are old. Population 1 stars belong to the disk component of the galaxy and are sometimes called disk population stars. They have nearly circular orbits in the plane of the galaxy and formed within the last few billion years. The Sun is a population 1 star, as are the type 1 Cepheid variables discussed in this chapter. And then population 2 stars belong to the spherical component of the galaxy and are sometimes called halo population stars. These stars have randomly tipped orbits ranging from circular to highly elliptical. They are old stars that formed when the galaxy was young. The metal-poor globular clusters are part of the halo population, as are the RR Lyrae and the type II Shepherds. Further observations show that there is a gradation between populations. Extreme population 1 stars are found only in the spiral arms. Slightly less metal-rich population 1 stars, called intermediate population 1 stars, are located throughout the disk. The Sun is an intermediate population 1 star. Stars that are even less metal-rich, such as stars in the central bulge, belong to the intermediate population 2. The most metal-poor stars are those in the halo, including those in globular clusters. Those are referred to as extreme population 2 stars. The two populations of stars in a galaxy are clearly different. You can see that in table 12.1. Those differences are clues to the history of the galaxy. So when you observe population 2 stars, such as those in halo, you are looking at the survivors of the early generations of stars in our galaxy. The first stars formed from gas that was metal poor, and only survivors of these early generations are low-mass, long-lived stars. Their spectra, which indicate the composition of their atmospheres, and not their cores, still shows the composition of the metal poor gas from which they formed. Population 1 stars, such as the Sun, formed more recently, after the interstellar medium had been enriched in metals, and its spectra shows stronger metal lines. Stars forming now have even higher metal abundances. So what is the age of the galaxy? So you are the same age as the universe because the matter can never be created or destroyed. Have you guys ever thought about that? Yeah, so you can just say age is really just a number. But how do you guys think we can determine the age of the galaxy? Because astronomers know how to find the age of star clusters. They can estimate the age of the oldest stars in the galaxy, giving a lower limit to the age of the entire galaxy. The process sounds straightforward, but uncertainties makes the easy answer hard to interpret. The oldest open clusters are 9 to 10 billion years old. These ages come from the turn-off points in the HR diagrams. But finding the age of an old cluster is difficult because old clusters change so slowly. Also, the exact location of the turn-off point depends on the chemical composition, which differs slightly among clusters. Finally, open clusters are not strongly bound by gravity. So all the open clusters may have dissipated as the stars wandered away. As it is reasonable to suppose that a galactic disk is somewhat older than the oldest remaining open clusters, which suggests the disk is at least 10 billion years old. Globular clusters have faint turn-off points in the HR diagrams and are clearly old, but finding these ages is difficult. Again, slight differences in chemical composition make noticeable differences when calculating the stellar models from which ages are determined. Also, to find the age of a cluster, astronomers must know its distance. Parallaxes from the Hipparcos satellite may allow astronomers to improve the calibration of the Shepard and RR Lyrae variable stars. And careful studies with the newest large telescopes have refined the chemical compositions and better defined the HR diagrams of globular clusters. The best analysis of all the data suggests that the average globular clusters are about 11 billion years old, though some globular clusters are younger than that, and some are older. Studies of the oldest globular clusters suggest that a halo of our galaxy is at least 13 billion years old. Observations of stellar populations and clusters show that a disk is younger than the halo, so you can combine these ages with the process of nucleosynthesis to tell the story of our galaxy. So here we can see clusters of recently formed hot stars in our galaxy, the ring of dust. Here we can see very distant young galaxies with a chaotic structure. Here we can see our dwarf companion galaxies, and that is the Large and Small Magellanic Clouds. Here we can see remote galaxies seen through the NGC 4911. Here we can see faint stars in the Milky Way, globular clusters. So if we put everything together we know, we can start putting everything together. So the lack of metals in a spherical component of the galaxy tells you it is very old. A fossil left behind by the galaxy when it was young and drastically different from its present disk shape. The study of element building and stellar populations leads to the fundamental question: how did our galaxy form? So if you look here we can see the galaxy from the top, you can see our sun. But if you look at sideways, you can see the edge view of the Milky Way. Here we can see the galactic center. So here we can see is young stars lies in this plane and older stars in this plane. So how did the galaxy form? So in the 1950s, astronomers began to develop a hypothesis, sometimes called the monolithic collapse hypothesis, also known as the top-down hypothesis, to explain the formation of a galaxy. So late observations forced the elevation of that hypothesis. So this is another good question for the test and exam. So here you can see at the top, a spherical cloud of turbulent gas gives birth to the first stars and star clusters. The rotation of the cloud of gas begins to contract towards its equatorial plane. Stars and clusters are left behind in the halo as the gas cloud flattens. New generations of stars have flatter distributions. Here we can see the disk of the galaxy is now very thin. So the monolithic collapse or top-down model for the origin of the galaxy begins with a spherical gas cloud that flattens into a disk. So the monolithic collapse hypothesis says that the galaxy formed from a single large cloud of turbulent gas over 13 billion years ago. That cloud contracted to form our galaxy. As gravity pulled the gas inward, the cloud began to fragment into smaller clouds. And because the gas was turbulent, the smaller clouds had random velocities. That caused the stars and star clusters that formed from these fragments to have orbits with a wide range of shapes. A few were circular, most were eccentric, and some were extremely eccentric. The orbits were also inclined at different angles, resulting in a spherical cloud of stars. The spherical component of the galaxy, of course. These first stars were metal poor because no stars has existed earlier to enrich the gas with metals. The second stage in this hypothesis accounts for the formation of the disk component. As the gas clouds in a regionally spherical cloud collided, turbulent motions in the gas cancelled out, as do eddies in recently stirred coffee, and a cloud was left with a uniform rotation. A rotating low-density cloud of gas cannot remain spherical. A star is spherical because its high internal pressure balances its gravity, but in a low-density cloud, the internal pressure is much too low to support a weight. Like a blob of pizza dough spun in the air, the cloud must flatten into a disk, eventually producing the galaxy's disk. This contraction from a sphere into a disk would have taken billions of years, and while that happened, the metal abundance gradually increased as generations of stars were born from the gradually flattening gas cloud. The stars and globular clusters of the halo were left behind by the cloud as it flattened. Subsequent generations of stars formed in flatter distributions. The gas distribution in the galaxy now is so flat that the youngest stars are confined to a disk only about 100 parsecs thick. These stars are metal-rich and have nearly circular orbits. The monolithic collapse hypothesis accounts for many of the Milky Way's properties. Advances in technology, however, have improved astronomical observations, and beginning in the 1980s, contradictions between theory and observations arose. For example, not all globular clusters have the same age, but surprisingly, some of the youngest clusters seem to be in the outer halo. In contrast, the monolithic collapse hypothesis says that a halo formed first and predicts that the clusters within it should either have a uniform age or the most distant one should be somewhat older. Another problem is that the older stars are observed to be metal poor but not completely metal free. There must have been at least a few massive stars to create these metals during each generation for the formation of the older stars now seen in a halo. Can the original hypothesis be modified to explain these observations? Astronomers suspect that a galaxy began as a large gas cloud containing almost no metals. Models of metal-free stars show that they are very massive, so that first generations of stars evolved rapidly and exploded as supernovae, which enriched the gas cloud with traces of metals. None of those massive first-generation stars survive, but the metals they created are detectable in the oldest population II stars. It seems likely that a central bulge and halo formed from such a gas cloud or from the accumulation of a number of gas clouds. A thick but low density disk of stars may have formed at this early stage. This would explain the age of the central bulge and the metals in both the older stars in the halo and those scattered above and below the disk. The thin part of the disk could have formed later as more gas fell into the galaxy and settled into the gas clouds of the thin disk where stars are forming today. Perhaps entire galaxies were captured by the growing Milky Way. Astronomers have found streams and rings of scattered stars surrounding our galaxy and hypothesize that they were produced when smaller galaxies were captured, pulled apart, and absorbed by a home galaxy. We will see dramatic evidence in the next chapter that such galaxy mergers do occur. So I can only imagine the headache these astronomers had to go through trying to figure out how things that are light years out of reach work. Yes, and that, if you remember, when we first started this module back in February, in the opening chapter, we had a discussion of scientific models. What is the scientific models? Why do we need scientific models? And that is exactly why we need to build up a model to try to explain what we can see and detect. So, question. So does the theory not assume that a galaxy begins as a sphere? Where would the sphere come from? So remember, that's actually a very good question. So if you don't have gravity pulling on something towards something, it will end up as a sphere. So have you ever thought why a raindrop is a sphere? If you, so raindrop falling, it's a sphere. If you put a blob of something in space or in a vacuum, it will end up as a sphere. It all depends what forces are working on it. But in nature, everything usually ends up as a sphere if no external force is acting on it. So if the young Milky Way galaxy in fact was partly assembled from stellar units, absorbing several small but partially evolved galaxies, in some of the globular clusters astronomers see in a halo may be hitchhikers. Astronomers now have evidence that our galaxy formed through merger of a number of smaller pre-galaxy clouds of gas and stars. plus late additions of infalling gas and more small galaxies. So, sir, why do so many things in space tend to turn into disks? So when it turns into disks is usually it depends on the rotation. So if you have a rotation of something, you have your, if it is spherical, that means while it's spinning, its equator will become bigger and bigger, and where the North South Pole is, that will become squished together. So thinking about it, an experiment you can do, if you take a piece of dough, so usually you can buy dough at Spar or Pick and Pay or any of those shops, that's usually round. But if you take that piece of dough and you start spinning it, you will see it become flat like a pizza disc. And that is exactly what happens. So it is due to your rotational forces on it and a bit of gravity. So yes, you are correct. That is described as Keplerian motion. So someone had a hand raised. So what forces of gravity act on galaxies? So what forces act is literally the nucleus or the center black hole. Because if you remember take for example our own solar system as example, we have the sun, everything orbits the sun, everything is rotating around the sun, and the sun is what's keeping everything in place. With a galaxy, that's the nucleus of the galaxy, and in most cases, it's a black hole. So here we can see the bottom-up galaxy formation. So you can see mixed clouds of normal and dark matter are drawn together. The first stars are massive, evolve fast, and begin making metals and dust as a large proto-galaxy accumulates. More clouds of dark matter plus gas, dust, and stars fall in and begin building a halo and a thick disk. Small galaxies are ripped apart by tides and absorbed, adding to the halo and disk. Then gas and dust settle into a thin disk where star formation continues. So, the bottom-up hypothesis for the formation of the Milky Way galaxy proposes that smaller star systems accumulated to form larger ones. To see how this could have built a galaxy, start with a top frame depicting the situation only a few 100 million years after the beginning of the universe. As small clouds of matter began accumulating and stars began forming in them. In the second frame, the central object has grown larger, and in a third frame, the galactic halo and disks are forming. By today, represented by the bottom frame, the disk of the galaxy has become very thin. So there is no external gravity acting on galaxies. No, there's no external gravity acting on galaxies. The only way there's external gravity that can act on galaxies, if as two galaxies approach one another, then the two galaxies would play tug of war between them with their gravitational fields, causing havoc, until one of them is basically engulfed by the other one. This bottom-up hypothesis for the formation of the galaxy would explain puzzles such as the observed ranges of globular clusters, ages, and metallicities. The metal abundances and ages of stars and star clusters in our galaxy seem to be important clues, but metal abundance and age do not tell the whole story. The astronomer Bernard Pagel was thinking of this when he said cats and dogs may have the same age and metallicity, but they are still cats and dogs. So here we are now. So our planet's hunting neighborhood. So most of the planets found to date lie within about 300 light years from our own sun. So if you put everything in perspective, this is where we are in compared to our own galaxy. So I'm going to end off this lecture slides with this quote. To boldly go where no man has gone before. Do you guys know who has said this or where this came from? Yes, you are correct. This is from Star Trek, one of my favorite shows ever. So, ladies and gentlemen, this was this lecture site. So let's take a 5-minute break before we continue with the next set of slides. So it's now 6:40. We will restart the class at 6:45. So question, how do we know what our galaxy looks like if we are in it? So that is a very good question. So as we discussed in just before recess, we know how other galaxies look like. We can observe mechanisms from other galaxies. So by observing other galaxies, we have an idea of how we would look like. So say for example, stupid example, say, for example, we didn't have mirrors on Earth, we didn't have cameras, we didn't have any material that can show our reflection. How would you know you would look like? You would look at the other people around you, and you will have more or less an idea of how you would look like. And that is exactly what we did with our own galaxy. So now question, so it's basically an educated guess. Yes is basically an educated guess. So if a photon is its own antiparticle, then why aren't they always annihilating each other? So that is a very good question. So I'm not a particle physicist, so I don't know much about this, but I will find out and report back tomorrow evening on that question. So that's so that's something I'm going to announce at the end of this class, but we can have our next quiz next week. But I will announce everything on ClickUp emails and all our groups. In question, sir, do you think the graviton is a dark matter's antiparticle? Yeah, for me it makes sense. So one other thing I want to talk to you guys So there's one thing I want to talk to you guys also about before we start our next set of lecture slides. In your third year, it doesn't matter what you are studying. It can be computer science, can be engineering. So engineering will be your fourth year. Physics you will do it. It doesn't matter what you are studying. In your final year, you are going to do a small research project called a mini dissertation. So for your research projects, you need to find a project and a supervisor for that project. And you will work the entire year on that project. So when it comes time at the end of your second year, you will need to pick a topic and a supervisor. But remember, you're going to work the entire year on that project and work the entire year of the supervisor. So make sure, number one, it's a topic that you will enjoy. And then secondly, also it's a supervisor you can actually work with. Because say you have a great topic and project, but you and your supervisor are bumping heads, then it's going to be a miserable project and a miserable year. But you can have a great supervisor, but horrible topic, and you will hate every moment of it. So I would suggest, when you have time, go introduce yourself to your different lecturers, find out what their research interests are. And when it comes time to do a project, then you know with who you would like to do a project and what project you would like. Because remember, usually at the end of each year, all lecturers needs to submit projects for students to do the following year. So if you are going to, usually beginning of your third year or end of the second year, you can just pick a project from a list, and whoever submitted that project, you get that as your supervisor, or beforehand, you are welcome to create your own topic as long as you have a supervisor that can approve it. So that's something just to think about in the future. So I'm not sure what you're studying, but usually you will do that for any course you are doing. So usually that forms part of your final year. So that's just something to keep in mind. So why do electrons act differently when observed? Does that signal consciousness? No, that doesn't signal consciousness. So for the consciousness, so that comes down to Schrödinger. You remember the experiment of Schrödinger's cat? Yeah, that's the uncertainty principle. So if you observed subatomic particles, if you know where they are, you don't know where they are moving, what speed they are moving. But if you know what speed they are moving, where they are moving, you don't know where they are. So that's the uncertainty principle. So, sir, are you one of the supervisors? So yes, I will be one of the supervisors. So it all depends on what you want to do. So if you're not bothered by anything and just want to get it over, you can pick a topic from a list, and that's your supervisor and topic. But usually about 6 months before your third year and before you need to do the project, you're more than welcome to reach out to your lecturers, find out what their research are, what you're interested in, and you can propose your own topic with a specific supervisor that you want. But that's just something to keep in mind. That's still 2 years away for you guys. So, sir, I remember once hearing that our galaxy will combine with the Andromeda. Are we combining with it, or is it tugging at us? So that is actually a very cool question. So when you do the math and you plot, so if you think about the universe, The entire galaxy is also moving. So we have the sun, our own, say for example, Earth. Earth is moving around the sun. But the sun is orbiting the center of our own galaxy. And the galaxy is also moving through the universe. So if you plot the trajectories of the different galaxies, the Andromeda galaxy and our own galaxy, the Milky Way, is moving towards each other. So right now, it's still too far away that we can feel any interactions, but we will discuss this in a later chapter as well. As the two becomes closer to one another, both will tug on each other. And then while they're becoming closer and closer and closer, the gravitational fields will cause havoc on one another until it eventually creates one bigger galaxy. Pleasure. So, in the previous sets of lecture slides, we discussed what a galaxy is, how a galaxy is formed. But within this, there are still a few different key differences. So with this lecture, we are now going to look at normal galaxies and active galaxies. But for us to understand, so sir, can I ask a question? You're more than welcome to ask a question. So with this is, to understand our galaxies, we need to understand a family of galaxies, just as we did the family of stars. How do we classify these different galaxies? Then we need to measure the properties of galaxies, speak about the evolution of galaxies, then discuss the active galactic nuclei and quasars. And then lastly, disks, jets, eruptions, and galaxy evolution. So it isn't related to work, but what is the purpose of an honorary degree? Okay, so that is, let me ask for you guys, do you guys quickly want a discussion on that? What is the difference between the different degrees and why it's necessary? Not a second major, what is the difference between a bachelor's, honors, master's, PhD? Okay, so one thing you get is your normal. There was something that was quite regularly in the past, but usually you did an associate's degree. That's a 2-year degree, but an associate's degree was replaced by a diploma. So that is, you get a broad knowledge to be able on a certain topic or field to do it. But then you get a bachelor's degree. So for bachelor's degree, you have a specific focused area and you learn general knowledge on it. So for example, if you do a BSc, that stands for Bachelor of Science. Let's take physics, for example. So if you're a Bachelor of Science in Physics, that means you have a broad background of physics, meaning you can do basically anything in any branch, or you have a basic understanding of anything in any branch of physics. So that means you have a basic understanding of nuclear physics, particle physics, astronomy, quantum mech, classical mechanics. You can do a bit of everything. But with an honors degree is you start to specialize into a specific field. So for example, if you want to specialize in, for example, astronomy, you do a Bachelor of Science honors degree in astronomy, meaning all the modules you take and classes you have will just be on astronomy modules. And then when you do a master's degree, it's meaning you, say example, you're doing a master's in astronomy, it meaning you are becoming now specialized in astronomy, meaning you are taking one little piece, one aspect of astronomy, and you are focusing on that. And then when you do a PhD, you even choose a smaller focus area of astronomy, and then you become the world expert on that. That is why you have a PhD. A PhD is for unique work. So if you pick something astronomy and do a PhD on it, then you are the world expert in the topic you've chosen in astronomy. So if you are working in industry, then usually for most places, a normal bachelor's degree is fine. Then you have the basic background and you can do your work. So take, for example, if you want to do software development or software engineering, then a normal bachelor's degree is fine. You have your normal background and you can continue. But if you want to be in a specific industry where you need a certain skill set, then you need an honors degree to build up that specific skill set. But if you even need a more specialized skill set, you will need to do a master's. So in the past, if you do a bachelor's degree, then you're fine. But these days, industry is looking at honors degrees. And if you're in industry and you have two people with the exact same experience applying for the exact same position, then a master's degree will be better than an honors degree. But if you want to work in academia, because academia is research-based, then you need a PhD. So question, so in your honors year, you will only be doing modules related to your course. So yes, so for example, in your honors degree, if you want to do a honors in astronomy, then you're just going to do astronomy modules. If you want to do for example, a honors degree in nuclear physics, then you're just going to do nuclear physics modules. And that's how it works. And then when it comes to academia, you get certain levels as well. So you just don't become a professor. So if you want to become a professor, you need a PhD, and then you need to do a certain amount of research. So if you have done a certain amount of research and a certain amount of publications behind your name, and you've supervised a certain amount of students, then you can get promoted to an associate professor. And then if you have done even more research, supervised even more students, and even get more publications and research behind your name, then you can be promoted to a full professor. So I hope that that answers a few of your questions. It's a pleasure. Yes, so I'm on course for my PhD, and I'm sure a few of you will do it as well. So is it difficult to be considered for a master's degree? No, it's not difficult to consider. It all depends on where you're going to study and what the minimum requirements are. So for it all depends. So the big difference is if you're undergraduate, it doesn't matter where in the world you are studying. Say, for example, you do Bachelor of Science in Physics. In undergraduate, it doesn't matter at which university you are, where in the world, the work will be the same, you are covered. You all have to do the same modules at undergraduate level. So you're all going to do Newtonian physics in first year, and in physics. It doesn't matter which university you are. So if you want to do a bachelor's degree, the university doesn't really matter. But as soon as you are looking at postgraduate qualifications, then a different university plays a big role, because certain universities have certain research groups and research fields where the employers or lecturers are specializing in. So say, for example, let's take UP for UP as an example. Say, for example, you want to work in microelectronics. Then UP is extremely good because UP has a well and founded microelectronics research group. But if you want to do, for example, renewable energy, then you go to UJ, because UJ has a very good group in renewable energy. For example, if you want to do photonics research, then UJ has a very, very good photonics research lab. But if you want to do semiconductor research and particle research, then UP has a very good research groups. That so depending where you want to do your master's and PhD, that is very important, and honors also. So yes, you're correct, and research. So UP is radio specialized. So we have optical astronomers at UP as well. But if you want to do more optical astronomy work, then you need to go to WITS and UCT. But here at UP, we look more at radio astronomy research as well. So cosmology, yes, we do cosmology at UP as well, and we do cosmology at WITS. So it all depends what you want to do. So that's where the specialized, where you need to go to do your master's and PhD programs. And it all depends on department to department. So usually we're in some degrees, if you want to do a master's degree, then you just need an honors. If you have honors, then you get entry into a master's program. But if you want, for some different departments, if you have honors, you need to have a minimum average of 65% to get entrance into the master's program, for example, but it all depends on faculty per faculty and department per department. So how about astrophysics? So yes, UP offers courses in astrophysics. We have a good astrophysics research group at UP. We also have a good astrophysics research group at WITS, at UJ, and UCT as well. So then you need to look at astrophysics. What part of astrophysics do you actually enjoy? And there you will need to find the appropriate supervisor at the appropriate university. So is it possible to do more than one honors degree? Yes, it's possible to do more than one honors degree. So you can do an honors degree, for example, in astrophysics. You can do an honors degree in nuclear physics. So it all depends on what you want to do. And yes, you can do more than one honors degree. So right now, recently, we have started a new research group at UP. It's collaboration between Department of Electrical Electronic Engineering and the Physics Department, where we are going to look at more at radio astronomy, where we are going to look at instrumentation development for astronomy. So we are going to look more definitely at astronomy signal processing, what I'm doing. And we are also going to look at correlation. And one thing we are also going to look at is wideband receivers. So wideband receivers is something that is quite a new hot topic in the astronomy world, because you don't want a receiver that only looks at a narrow band of the electromagnetic spectrum. You want one receiver that can look at a wider range of the electromagnetic spectrum. And that is what we have received now permission to start a new research group, and we've also received funding for the group. So that is actually now happening. So do other countries have honors degrees? In other countries only have masters and PhD only, but not honors. So yes, that is something depending on the system we are following. So if you look at the Commonwealth countries, so that means all the countries that form part of the British Empire have honors degrees. So basically an honors degree is your 4th year. So am I right, you have to do your honors before masters? Yes, you have to do your honors before masters. Your honors is, yes, you have to have honors before you can do a master's. So some degrees, say for example, LLB, law. So you don't hear people do honors in law, because the law degree is a 4-year program. So that means you don't get your degree on a bachelor's level, you receive it on a honors level. So that is why from an LLB, you can directly do an LLM, for example. In say, for example, the engineering department. So UP is the only university that offers a separate honors degree for engineering, but other universities, you get your degree on honors level. So you do a BEng, you get an honors level, and you can directly do a master's. So Usually in countries such as the former Commonwealth countries or Commonwealth countries, you do your bachelor's, your honors, your master's, your PhD. But in other countries such as the US, they don't use the honor system, so they have the 4-year degree. So you do your 4-year degree that you get on honors level, so basically honors degree, then master's, then PhD. And you get paid for PhD masters or paid by yourself. So it's a degree you're enrolled for, so you have to pay for it. But usually on master's level, about 99% of the time, you apply for a master's or PhD bursary. That bursary will pay for your research, and that bursary will pay you you call it a salary each month that you live from. Okay, cool. So far from this edition, we have gone through all 20 lectures. So for our, no, not all 20 lectures, I will break it down in the scope for you guys. So talking about this stuff is stressful. No, it's not stressful. You get a hang of it. So what all are we writing? So it's going to be an online test. So you guys probably recognize this image. So will it be open book? No, it won't be open book. It will be a closed book test. Yes, the exam will also be online. Pleasure. So do you guys recognize this image? Yes, you are correct. This is taken by the Hubble Space Telescope. And this is the Hubble Deep Sky image. If you just Google the Hubble Deep Sky image, you will get it. So is this the photo taken of the one tiny dark spot? Yes, that is. So this is in the night sky, one of the most darkest spots. I can't remember where it was, but it was just somewhere beside the moon somewhere. But with the naked eye and through smaller telescopes, it seems like there's nothing there. But then Hubble took a picture, and everything you see in this image is a galaxy. So look at all these different and beautiful galaxies. So instead of these two dots are two stars in the foreground, but the rest are all galaxies. And from this, we can see galaxies comes in different colors and different shapes and sizes. So from this, we need to build up our family of galaxies the same way we did as our family of stars. Yes, a 10-day exposure time. I know it is extreme. So Milky Way galaxy is only one of the many billions of galaxies visible in the sky. This chapter will expand your horizon to discuss difficulties, different kinds of galaxies, complex histories, and violent eruptions. So I'm just looking here if I missed any other comments. Yes, Miss Kutsia, you are more welcome to come to a consultation session to talk about different ideas. You're more welcome to pop in any time or just send me an email and we can set up a consultation session. So just come back to consultation. I will be on campus tomorrow from about 9:30 to 1:30. I just need to leave campus on 1:30 because I have a different appointment off campus at 3 o'clock. So you're more welcome to pop in during that time. And then if you want me on campus for other consultation sessions, just send me an email and I'll set up basically a time and date anytime other than Mondays and Tuesdays as well. So here you can expect answers to 5 important questions. So 1, what are the different types of galaxies? 2, how do astronomers determine distances, sizes, luminosities, and masses of galaxies? Thirdly, Do other galaxies contain central supermassive black holes and dark matter, as does our own galaxy? 4. How do collisions and interactions affect the evolution of galaxies? And then lastly, how did supermassive black holes in a galaxy nuclei form, evolve, and affect host galaxies? Do these questions look familiar to you guys? These are almost the exact same questions we asked about stars. So remember, we asked what are the different types of stars, now what's the different types of galaxies? So every time I hear a supermassive black hole, the song Muse plays in my head. That is a song I've heard a long time ago, and if I'm not mistaken, that song always aired or came out more or less the same time as the Twilight series. So when we talk about our different galaxies, we have a few different galaxies. So these are all classifications I could ask for test and exam. So we have our bed spiral galaxies, our irregular galaxies, our spiral galaxies, peculiar galaxies, elliptical galaxies, and lenticular galaxies. Now, not a Twilight series. So the Twilight series is supposed to be the same as Black Mirror, but the Twilight movies with the werewolves and vampires. So is it peculiar? Yes, it is peculiar. That's why it actually received the name. So something you will realize is astronomers aren't very good at naming things. So usually it's named at what they see. So it's peculiar, let's call it peculiar galaxy. But that is something we will discuss in this chapter as well. So science fiction heroes effortlessly between the stars, travel between the stars, but almost none travels between the galaxies. As you leave your own galaxy, the Milky Way, behind, you will voyage out into the depths of the universe, out among the galaxies, into space so deep it is unexplored even in fiction. So why do you guess in sci-fi movies they don't leave the galaxy or don't explore different galaxies? Not because it's scary, it's very empty, but if you want to leave the Earth, we need an escape velocity to escape the gravitational pull of the Earth. If we want to leave our solar system, we will need the escape velocity of our solar system. So if we want to leave our galaxy, we need to achieve the escape velocity to leave our galaxy as well. That's the one thing. And the second thing is the galaxy is so big, we don't have the technology to even leave it. So even in Star Trek Voyager, when Voyager got flung to the other side of the galaxy, it took them almost 60 years to get back. So that is why. And that is why it is a unique topic as well to talk about. So in sci-fi movies, we would jump into Millennium Falcon, go to hyperspace and explore our own galaxy. But to explore different galaxies are a different story on its own. So astronomy books often include pictures of spiral galaxies. Like movie stars, spiral galaxies get a lot of attention because they are beautiful. But many galaxies are nearly featureless, clouds of stars, and others are distorted muddles of gas and dust. You must begin by sorting out this jumble of galaxies. So here we can see, a century ago, photos of galaxies looked like spiral clouds of haze. Modern images of these relatively nearby galaxies reveal dramatically beautiful objects filled with stars plus clouds of gas and dust. So here we can see young blue stars illuminate the spiral arms. Here we can see clouds of gas and dust in a small foreground galaxy visible and silhouetted against the background galaxy. Here we can see dusty disk of a galaxy warped by the interaction with another galaxy, and new stars forming in the dust clouds. And here we can see dust clouds glow red in this infrared image. So astronomers classify galaxies according to their shapes in photographs made at visual wavelengths using a system developed by Edwin Hubble in the 1920s. Such system of classification are a fundamental technique in science. So firstly, many galaxies have no disk, no spiral arms, and almost no gas and dust. These elliptical galaxies, so class E, range from huge giants to small dwarfs. And secondly, disk-shaped galaxies usually have spiral arms and contain gas and dust. Some of these spiral galaxies, classified as, have a central region shaped like an elongated bar and are so-called barred spiral galaxies, so abbreviated SB. So you learn in chapter 12 that the Milky Way galaxy is a barred spiral. A few disk galaxies contain relatively little gas and dust. These are called lenticular galaxies, class S0. Finally, notice that the irregular galaxies, class I, which are generally shapeless and tend to be rich in gas and dust. It is surprisingly difficult to figure out what proportions of galaxies are elliptical, spiral, or irregular. In catalogs of galaxies, about 70% are spiral, but that is misleading because spiral galaxies contain hot luminous stars and clouds of ionized gas that make them easy to notice. Most ellipticals are fainter and harder to notice. Small galaxies, such as dwarf ellipticals and dwarf irregulars, are actually very common, but they are hard to detect. From careful statistical studies, astronomers estimate that ellipticals are actually more common than spirals, and that irregulars make up about 25% of all galaxies. So how many galaxies are there? Long exposure images of small areas of the sky are called deep fields because they detect the most distant galaxies deep in space. So here we can see in this image an apparently empty spot on the sky, only 1/13 diameter of the full moon, contains more than 1,500 galaxies in this extremely long exposure known as the Hubble Deep Field North. Only 4 stars are visible in this image. They are sharp points of light with the diffraction spikes produced by the telescope optics. Eventually, the entire sky is similarly filled with galaxies. So what are the properties of galaxies? What are their diameters, luminosities, and masses? Just as our study of stellar characteristics, the first step in your study of galaxies is to find out how far away they are. Once you know a galaxy's distance, its size and luminosity are relatively easy to find. Later in the section, you will see that just as for stars, finding the masses of galaxies is more difficult. So now we're going to start using almost the same principles. We need to know how far away it is, the luminosities, its size. Then we can determine everything else. So ladies and gentlemen, I see we have 2 minutes of this lecture left. So let's call it night. We will continue tomorrow night of this lecture, and then we will discuss the different properties of galaxies. So remember, I will be on campus tomorrow for consultation. We will have a quiz next week. I will upload information on that in the next day. Otherwise, you guys are more than welcome to log off. Have a great week, and I'm sure everything will go well for the second quarter. So have a great evening, everyone, and I will see you in tomorrow night's class. So which room and building will you be in? I'm in Natural Science 1 building, 5th floor, office 68. Will the quiz for next week do before the start of next week, or will it be next week? So we'll be open next week, so most likely open next week Monday and close the following Sunday. So question about the project. Can I edit NASA image to represent my observations? Unfortunately not. You will have to do your own observations. So for tomorrow, I will be in my office from 9:30 to about 1:30 in the afternoon. So I mean only the image afternoon because my drawing is bad. So you can add it above your drawing. So you can do your drawing and then you can add that with your drawing. Pleasure. So I'm going to remain active for another minute or two if you guys have more questions. So should you read A Free Body Problem? Probably my favorite sci-fi book series ever. I will definitely read it. Awesome. So if there's no more questions, then I'm also going to log off. Have a great evening, everyone. I will see you all in tomorrow night's class. Good evening, everyone.